Welcome to Mentivia. Today we're diving into one of the most important concepts in chemistry, valence electrons and their role in chemical bonding. Hi, I'm Mark from Mentivia.com. In this video we'll explore how valence electrons, the outermost electrons in an atom, govern the way atoms bond and interact. These electrons determine whether atoms will share, donate, or attract electrons from others, forming the basis of molecules and the properties of matter. By understanding how valence electrons behave, you'll gain insight into why elements form specific compounds, how reactivity is predicted, and what drives the structure of everything from water to DNA. Let's uncover the chemistry behind connection. So, what exactly are valence electrons? They are the electrons found in the outermost electron shell of an atom. Unlike the inner core electrons, which are tightly bound to the nucleus, valence electrons are relatively loosely held. This makes them readily available to be involved in chemical reactions, either through sharing or transferring. Their number and arrangement dictate an atom's chemical properties and its reactivity. The primary driving force behind chemical bonding is an atom's inherent desire to achieve a stable electron configuration. Think of it as atoms seeking a state of contentment or balance. This stable state is most often achieved by resembling the electron configuration of a noble gas, which are elements known for their exceptional stability and lack of reactivity. Noble gases, like neon or argon, have a full outer electron shell, typically with 8 valence electrons, a state referred to as a stable octet. This complete outer shell represents a very low-energy, highly stable arrangement. Atoms that don't have this full outer shell will gain, lose, or share electrons to attain this coveted configuration, following what's known as the octet rule. Let's look at an example, sodium. Sodium has 1 valence electron. To achieve a stable noble gas configuration, it's much easier for sodium to lose that single electron than to gain 7 more. When sodium loses 1 electron, it forms a positively charged ion, Na+, and its electron configuration becomes identical to that of neon, which is 1s2, 2s2, 2p6. This loss makes it stable. Now consider chlorine. Chlorine has 7 valence electrons. To achieve a stable octet, it needs to gain 1 more electron. When chlorine gains 1 electron, it forms a negatively charged ion. Its electron configuration then becomes 1s2, 2s2, 2p6, 3s2, 3p6. This gaining of electrons allows chlorine to reach its stable state. These examples illustrate 2 fundamental types of chemical bonding. When electrons are completely transferred from one atom to another, as seen with sodium losing an electron and chlorine gaining them, we call this ionic bonding. This typically occurs between a metal and a nonmetal, creating oppositely charged ions that are strongly attracted to each other. In contrast, covalent bonding involves the sharing of valence electrons between atoms. This usually happens between 2 nonmetal atoms that both need electrons to achieve a stable configuration. By sharing, both atoms can effectively count the shared electrons towards their own stable octet, creating a strong bond that holds them together in a molecule. The number of valence electrons an atom possesses is a powerful predictor of its bonding behavior. Elements with very few valence electrons, like group 1 and 2 metals, tend to lose electrons and form ionic bonds. Elements with nearly full valence shells, like group 16 and 17 nonmetals, tend to gain electrons and also form ionic bonds. However, elements with intermediate numbers of valence electrons are more likely to share them, leading to covalent bonds. To summarize, valence electrons are the outermost electrons that drive chemical bonding. Atoms bond to achieve stable electron configurations, typically by resembling noble gases through the octet rule. We saw how sodium loses an electron and oxygen gains electrons to form ions, leading to ionic bonds. We also discussed covalent bonding, where electrons are shared. Ultimately, an atom's valence electron count is key to predicting whether it will form ionic or covalent bonds. Thanks for watching. If this video helped you understand electron arrangement, there's plenty more waiting for you at Mentivia.com. Free e-learnings, videos, and articles designed to take your science knowledge to the next level. And if you're serious about learning, don't forget to hit that subscribe button. It's the best way to stay connected and make sure you never miss a new video. We've got lots more coming your way.